Hello, in this video we're going to continue going over the chapter 5.1 lecture slides. So in the last video I didn't get to finish going over the standardized statistic. So this idea of a z-score standardization takes the statistic, whatever it may be, mean or proportion, you subtract the null hypothesis, whatever that may be, and then divide it by the standard error. So Z gives you, the number of standard errors away from the assumed null hypothesis. And the idea is if the Z-score is very, very far away from the null, then we're going to reject the null hypothesis. If it's not too far away from the null value, then we do not reject the null hypothesis. So going on the last example with malaria and mosquitoes, our statistic, the p-hat, or difference of proportions, p-hat minus p-hat, we got to be a minus 0.131. The null value is 0. We assumed no difference in the two proportions. And from the randomization distribution, we got a standard error to be about 0.056. This is a measure of the spread of the sampling distribution, or the measure of spread of all possible statistics. So if we throw this into the formula, we get the statistic minus 0.131 minus 0 for the null hypothesis divided by the standard error, and we get a minus 2.34. Okay, so I have this in the next slide, but I want to show minus 2.34. If we go over to stat key and click on the normal distribution, the idea of a standardization, that z-score means we keep the mean at 0 and standard deviation at 1. And since we got a negative value, I need to click left tail and type in minus 2.34. Larger, minus 2.34. Click OK. And notice right here we get a p-value of 0.0096. Again, it's not the exact same value as the randomization distribution, but it should be fairly close. All right, so like as I said, I should show on the stat key that in standard normal distribution, you always have the mean equal 0 and standard deviation equal 1. You use the standard normal when you're using z, notationally n parentheses 0, 1. That's that normal distribution. And going back right here, so again, I showed it on the screen, but make sure that mean is 0, standard deviation is 1. If a statistic is normally distributed under the null hypothesis, the p-value can be calculated as a proportion of the normal distribution beyond. So the idea is how far is z from 0? And here we show that we have 0 when we standardize. 0 is always going to be the center. The z-score is going to go on the x-axis, and then p-value is going to go on the area underneath the curve. All right, so kind of looking at this process, we take a randomization test, which we've been doing in chapters 4. Replace that symmetric bell-shaped looking distribution with a smooth curve. And notice in here we got a slightly different p-value, 0.009 versus 0.0097. And this right here is with the statistic. We could standardize and get roughly the same exact value, minus 2.34 is the standardized z-score, and 0.0096 is the p-value. And I'm going to have a video, after I go through these slides, going over the standardization a little bit more. P-value is always proportion in the tail beyond the relative statistic. In this case, since that p-value is so small, we would reject the null hypothesis, even at a 1% level. We have evidence that mosquitoes exposed to malaria parasites are less likely to approach humans before they become infectious. All right, so malaria and mosquitoes, the parasites, the malaria parasite would benefit if mosquitoes approach humans less often after being exposed, but before they could spread the infection. And then once they spread the infection, are they more likely to approach humans? So does infecting mosquitoes with malaria actually impact their behavior this way? What we just did is the first part of the study. Actually, yes, we rejected the null hypothesis and concluded there's enough evidence that mosquitoes do approach humans less often after being exposed, but before they could spread the parasite. So then now we need to go into the second part of this study. What happened after the 8 days when mosquitoes could spread the parasite? So if we're looking at data, again, the hypothesis is once the parasite could spread, we want to know, does the parasite somehow affect the mosquitoes and make them more likely to approach humans to bite? So here we have the null hypothesis. Has to be one of these first two. We assumed the control group is the same as the proportion of the exposed group. But now in this case, we think the exposed group, the proportion that approaches humans, that tries to bite humans, is going to be greater than the control group. So remember, this control group does not have the malaria parasite. The exposed group does. So looking at the data for before infections, we got the minus 0.131. After infectious, so this is at least 9 days later, when the mosquitoes can spread the disease. You'll notice the difference here is going to be positive. This means the infectious or the exposed group has a 15% more likelihood of approaching humans, at least according to this study. So the evidence so far, the bare evidence seems to suggest that the parasite does seem to affect the mosquitoes in some way. All right, so if we look at the difference in proportion is 0.15, we're down at, and the standard error is 0.05. Again, we would need to go to StatKey to get this exact value, but assuming you have the standard error, is this significant? All right, I think this is not an easy question. Answer is yes, but why is it significant? So here's that Z-score. Z is your statistic, 0.15, minus the null, but there's no minus here because we're assuming the null is zero difference in the two proportions, divided by your standard error. 0.15 divided by 0.05 is 3. And look over here, if we look at the normal distribution, this 3 represents the number of standard deviations away from the mean, or how far is the sample statistic from 0. And notice this is not likely to happen. Kind of look over here. Visually, this is unlikely to happen. So that's why we're going to say this is a fairly significant result. So we would yield a low p-value, because again, this is unlikely to happen. All right, in general, if we're above 2 standard deviations, the 2 or 2, these are always significant at a 5% confidence level. So it appears that mosquitoes affected by malaria parasites do in fact behave in ways advantageous to the parasite. So do they change the brain chemistry of mosquitoes, the DNA? How do they do this? I don't know. But at least with the study, exposed mosquitoes are less likely to approach before becoming infectious. So the parasite wants to keep the mosquito alive. And after the mosquitoes could spread the disease, they are more likely to approach humans after becoming infectious. So if the if the malaria parasite does not affect the mosquitoes, we would not have seen results as extreme as we did. And more recent research is looking at toxoplasmosis, a parasite that impacts rat and human behavior. There have been studies where rats that have this disease actually in some ways commit suicide and try to get eaten by different animals such as cats and whatnot. And the thought is, well, why are these rats trying to kill themselves? It's the parasites affecting the brain chemistry of the rat, making it likely to spread the parasite. So if another animal eats the rat, then they'll carry the parasite through. So this is a fairly new area of study, getting this detail about these parasites. Of course, for hundreds of thousands of years we've known about parasites, but now researchers are looking at, do parasites actually change the brain chemistry of their hosts, or at least change their behavior? I think it's pretty interesting and a little bit sci-fi-y. Anyway, so to find p-value from this excuse me, the standard normal distribution. Don't forget this n parentheses 0, 1 means the normal distribution, mean of 0, standard deviation 1. If the distribution statistic is normal, we compute a z-score, sample statistic minus the null value, divided by the standard error. Compare that z to the normal distribution at 0, 1 to compute a p-value. Keep in mind, the statistic is from the data. The null value is from the assumed to be true null hypothesis. And for right now, the standard error is from a randomization distribution. Doing those bootstrap distributions. In chapter 6, we'll talk about formulas to actually compute standard error. Okay, so another question. Are firstborn children actually smarter? I would hope not, because I'm not the firstborn child. So the explanatory variable, firstborn or not, so someone firstborn child or not firstborn. Response variable, looking at combined SAT score. So this study was done on college students, which makes sense. College students have to take SAT scores. So based on a sample of college students, we find that the average score of the firstborn minus the average score of the not firstborn is 30.26. So you can interpret this as saying the firstborn person does 30 points higher on average than the not firstborn. And from randomization distribution, we find the standard error is 37. So at a glance, you might think, well, this is maybe a big difference, 30 points difference, but the standard error measures the spread of all these statistics. All right, so before we do anything, what is the standardization test statistic? Again, this is that z-score. You want to practice this, pause the video and go compute the z-score. Up here, we take the statistic, which is at 30.26. The null is 0. In this class, we're always going to assume if we're doing a difference of means or a difference of proportion, the null is 0. And divide by 37 to get 0.818. All right, standardization test statistic is 0.818. What is the p-value? Here we would get the p-value to be about 207. So where does this come from? That standardization statistic is 0.818. If I go into stat key, we want the normal distribution. If you're doing the standardization, the z-score, you keep these at 0 and 1. I'm going to click on right tail. And down here, I just need to change this value to that 0.818. Click OK. And that's where that p-value comes from, 0.207. All right, so what does that mean? We do not have convincing evidence that firstborn children are smarter. They did score 30 points better on average than the not firstborn in the sample. But this p-value is not very low. It's not less than 10% or 5%, so we would not reject the null hypothesis. It could just be, random luck that the firstborn in that sample did better than the not firstborn. All right, as a summary, if your distribution of statistics is normal, we've got that z-score, sample stat minus null value divided by standard error. We're going to compare that z to the normal distribution at 0, 1 to compute p-value. Okay, and in the next video, I actually want to spend a little bit of time. I'm going to go outside the standard class slides, and I want to go into this z value some more, because I think a lot of students get confused on this. But that'll be in the next video.